Perfect timing, somebody just arrived. Well, we're going to be doing a new section called section 4.2, and this is, the heading for the section is the mean value theorem, but it's actually got two theorems inside it. The first one we're going to look at is called Rolle's theorem, after a guy called Rolle, and the second one's called the mean value theorem. So let's focus on the first one, called Rolle's theorem. And what Rolle's theorem says is, if you have a function, f of x, and it's continuous and differentiable, in this case on the interval from a to b, then there will be a number x equal to c such that the derivative at c will be 0. Oh, and I've also forgot to add in that f of x is continuous and differentiable in A and B, and the f of a is equal to f of b. Then there's guaranteed to be a number c such that f dash c is equal to 0. So here's my picture. That is a nice curve. Would you agree? Nice curves are continuous. What's not continuous? Remember the holes and the jump discontinuities and vertical asymptotes, right? This function is differentiable. What that means is I can pick any point in that curve, and won't I be able to get a tangent line? Lastly, this function starts and finishes at the same height, right? So f of a and f of b, same value, is it? Now, according to Rolle's theorem, then there's guaranteed to be a number c, for instance, there's going to be one here, where the derivative is 0. In this particular case, isn't there two possible places for c? But Rolle's theorem says there's guaranteed to be one. Does the logic of that make sense, that if you start and finish at the same height and it's a nice curve, don't you have to be a hill or a valley somewhere? Unless it's a straight line, right? In which case, every single point has a slope of 0, right? That makes sense? Right. So what do you get as a question? Basically, you get a function and an interval, and it says to you, check that you can use Rolle's theorem, and then find the missing c. So most of the questions tend to be check that you can use the theorem, and then secondly, find the missing value of c. So I'm going right in and finding a question that's not a visual one. Here we go. It is version of question 3. And the function is x cubed, take away 4x squared, take away 16x plus 2, and the interval is from -4 to 4. Now, a lot of the original check is basically obvious. Would you agree that that's a cubic equation? Don't the cubic equations go up and down, right? They look like a big ziggy-zag. Aren't cubic equations continuous and differentiable, right? There's no weird things happening. So all I need to do now is call that A and call that B, is I find out the value of the function at the start, and I find out the value of the function at the end. And you're just going to have to trust me on that this guy is -62 and this guy is -62. So can I use Rolle's theorem? Is it continuous? Yes. How do I know that? It's obvious. Is it differentiable? Yes. How do I know it? It's obvious, right? There's no a calculation to prove it. The value of the function at the start and the value of the function at the end are the same number, right? They're both -62. So according to Rolle's theorem then, shouldn't we be able to find the missing c, right? Some place that has a derivative of 0. So what you do now is find the derivative, which is 3x squared, take away 8x, take away 16, and make it equal to 0. And when I solve this equation, the values of x, where this is true, as long as they're inside this interval, that's the c that we're being asked to find, right? The x coordinate that has a derivative of 0. I would look at this guy and say, it looks to me like it's going to be a factor. I'm looking at 16. I know there are lots of ways of getting 16, but I'm pretty sure it's a 4 and a 4. Anybody want to finish off with the plus minus combination? And we'll see what we get. Plus minus 4, plus minus 4. What would generate this?
Plus 4 and then minus 4.
Okay, so I'll put a minus 4 here, plus 4 here. We agree? Check it out, foil it. Yep, it works. So this guy here, when is it is equal to 0? It's equal to 0 when x is negative 4/3. And this guy here, it's equal to 0 at 4. So far, so good. Except this magic number is not allowed to be either of the endpoints. And the reason it's not allowed to be either of the endpoints, would you agree at the ends here, the function isn't a hill or a valley, it just like stops. So the number that you must pick is any number that's between the limits. So you can't pick negative 4 as an answer, you can't pick 4, but anything that's in between, in this case, there's only one. So in this case, your C would be negative 4/3. Any questions about that? That all you are really going to be doing is first proving that you can use Rolle's theorem by just saying, yeah, it's continuous and differentiable. Find the value at the start, negative 4. Find the value of the function at the end, 4. If they're equal, Rolle's theorem is good to go. Differentiate it and then solve for 0. Only choose the solutions that are inside the range. Can't use the ends, must be inside it. Let me try and see if we can visualize that this actually does work. So I'm going to go here and I'm going to do y equals, and it's going to be x cubed, and take away 4x squared. Take away 16x, add 2. We're only interested in x between negative 4 and 4, so I'm going to go negative 4 less than or equal to x less than or equal to 4. There we go. Maybe shrink it up a little bit. There we go. I'd probably go here and change the x's to be what? Negative 4 to positive 4. Okay, and click off that. And I need y is probably about 20, negative 20 would probably do it. Okay. I'm just tweaking the x and y, fellas. There we go. Click on that. Right, can you see the start and finish? Right. Would you agree that right about here, isn't there a horizontal tangent line? And that is negative 4/3. And that guy is negative 1.333 is negative 4/3. Do you see it found it? Inside that interval. And we call that Rolle's theorem. Let's move back to my white thing and see if I can find another one. Suppose f of x is a quadratic. And there's our interval. Quadratics are continuous and differentiable. We're going to find the value at the start A and the finish B. And at the start and the finish, what do we get here? Don't know yet. Negative 1, that's 3, that's 6, that's 0, and that's 9. That's 3. 3 3s is 9. Take away 18 is 9. Oh, merge check. I can't count today. Let's just do it in a calculator. That way I won't screw up. That's 3. That's add 6. Oh, it's add 6. That's what I did wrong. Okay, now it works. That's 12 and that's 12. So, continuous, check. Differentiable, definitely, check. Is the starting value the same? Yes. We can use Rolle's theorem. So that means find the derivative. When is it 0? It's 0 at x equals 1. And is that in the range? Yes, it is. We're done. Now I'm going to show you one where Rolle's theorem might have a problem. This is question 6. The function f of x is 1 take away x to 2/3. And I should have Rolle's, I should have Desmos all set up. And let me show you why this function cannot be done using Rolle's theorem. So are you looking at Desmos right now? Okay, so the function that I am going to look at is 1 take away x to the power of 2/3. Now I'm going to zoom in at 0. Can you see a funny little, like the roof of a house? Do you see a little peak? At that point at x equals 0, the derivative does not exist. You cannot find a tangent line at one of those peaks. And because it's not differentiable at that point, we cannot use Rolle's theorem. And that's essentially what that question is about. So let me try and show you what's going on. It looked like that. And I'm saying no derivative here. And you might think, well, isn't it a horizontal line? Not really. If you come in from this side, the tangent line looks like that. And if you come in from this side, it looks like that. In other words, depends on which part of the curve. Can you see that the tangent lines are not agreeing with each other, right? And if it is not differentiable, even at one point, Rolle's theorem is out. So that means you cannot use Rolle's theorem if there's a vertical asymptote between the start and the finish. You cannot use Rolle's theorem if there's a jump discontinuity. You cannot use it if the derivative doesn't exist. So you might want to plug some of them into Desmos to have a look, just in case you've got one that doesn't exist. For those people who like to know names of things, whenever a curve meets a point like this, that's called a cusp, C-U-S-P. So a cusp. And that would be the reason for that one not being allowed to use Rolle's theorems. Seven is Rolle's theorem, that's good. Let's do question 8. And the function that we're going to do Rolle's theorem on is this function here. And the interval is in that range. Now, when I do the test for Rolle's theorem, I have to remember that we only are interested in what it does in this range. Would you agree this function has a problem at 0? But since I'm not using 0 in my interval, I can ignore that. As long as it's not 0, isn't this curve okay? So it's differentiable and continuous in this range. Yeah. If you find the value of the function at the start and you find the value of the function at the end, the a and the b, you get 9 1/9, which is 82/9 in both cases. Which means Rolle's theorem works, right? It's continuous and differentiable in this interval, and the value of the function at the start and the value of the function at the end are both the same number. So I'm now going to find the missing c, the place on this curve that has a 0 derivative. Okay, let's start off with, what will I rewrite 1 over x as so that I can differentiate it?
X to the -1.
Yeah. Are we getting, the more this happens, I hope the more comfortable. Whenever you see a square root now, don't you think x to the half if you're going to differentiate it, right? If you see a cube root, don't you think of x to the third? If you see 1 over x, you think x to the -1, right? That's kind of part of the process that we get more comfortable with. So the derivative is 1 multiplied by the power. Oops, I'm doing too much at once there. Multiply by the power and then reduce the power by 1. And then make it look pretty. Not a lot going on here. How about just call it that? Now I need to solve when is it 0. How about adding 1 over x squared to both sides? Okay, you tell me now, where should I go algebraically to find x to solve this equation?
Multiply both sides by x squared.
Okay. And what are the answers now? What are the x's at work?
X equals 1.
Anything else?
X equals -1.
Okay. Now she may well have already done this, which I like if she did, but -1's no good. Why is -1 no good in this situation? Why can't I use -1?
Because of the interval.
That's it, because of the interval. That's the only reason. So in this case, there's only one guy for c, c equals 1. And that is the end of Rolle's theorem. Are you comfortable that if I give you a function where it starts and finishes at the same point, right, same height, and it's continuous and differentiable, that you can use this guy called Rolle's theorem? And that means that there's going to be some place, at least one place, where the derivative is 0. We feel good with that kind of question. Right. So let's move on, to the second one. And the second one is called the mean value theorem. very often MVT for short. The mean value theorem is an extension of Rolle's theorem, right? It's a more general version. So what you have is your typical continuous and differentiable curve, right? Starts here, right? And then it finishes say up there. And your function, right? Y equals f of x. So if f of x is continuous and differentiable, on the interval a to b, which it definitely is, then there will be a number x equals c again, such that f dashed of c is equal to this. So that guy there is the value of the function f of a. This guy up here is the value of the function f of b. We are saying that there is a slope, right? A tangent line, right? A slope of a tangent line that's equal to this. And if you're wondering what on earth this guy is, if you join the start to the finish, you see that line from the beginning point to the end? The slope of that red line is f of b take away f of a, the rise, divided by b minus a, the run. So you can basically, the slope of that line is him. So what this is saying, the mean value theorem says, if you have a continuous, nice differentiable function from a to b, there is some point, at least one point in this curve, my guess is it probably be about here, that has a tangent line the same as that guy. So this fella here would be C. Does the logic of that make sense? That if you start somewhere and you go and do your thing, there's going to be at least one place parallel, right? The same slope as the line joining the start to the finish.
Yes, and we've used this formula before too.
We have. This is the rise over run formula being used in a different way. So you're going to check it, and you're going to check it by the usual, it's obvious, right? Is it continuous and differentiable? But you don't care. In fact, would you agree that most of the time the start and finish heights are going to be different? If the start and finish heights are the same, don't you end up with Rolle's theorem? Because if it starts and finishes at the same number, won't this fraction be equal to 0? And that's what Rolle's theorem says. So Rolle's theorem is really just a special case of the mean value theorem. So let's put it into operation then. Question 9. The function that we're going to do the mean value theorem on is 5x squared take away 3x add 2, and it's going to be in the interval 0 to 2. So that's basically my A and my B. Would you agree that all quadratics are continuous and differentiable? Right, so we can use the mean value theorem. I'm going to find the value of f of b take away f of a over b minus a. Let's get that as a number. So it's going to be the value of the function at 2, take away the value of the function at 0, divided by 2, take away 0. The value of the function at 2 is going to be 20, 22, take away 6, 16. The value of the function at 0 is going to be 2. So that's going to be 14 over 2, so it's 7. So the slope from the start to the finish is 7, right? So you can imagine that red line there would be a slope of 7. So we need to now find the derivative, which is basically 10x, take away 3. And we are after, when is the derivative equal to this number, 7? Well, how about add 3 to both sides and then divide by 10? And that guy is our C. So the mean value theorem says that there's at least one point on this curve between 0 and 2. You're not allowed to use 0, 2, but between 0 and 2, that has a slope the same as this number here, which in this case happens to be 7. Right. We call this number C. Right? It's just the x coordinate, but we call it C. Are we good on that one? Any questions before I move on to number 10? Okay. Question 10. It's a cubic function. And the interval is going to be from -2 to 2. So there's my A and my B. Let's check it. Continuous, yep. Differentiable, yes. Why? All cubic functions are continuous and differentiable everywhere, including between here and here. So let's find the value of f of B, take away f of A over B minus A. In this case, it's going to be the value of the function at 2, take away the value of the function at -2, and 2 take away -2. 2 add 2 gets me 4. 2, 8. 8 take away 6 is 2. 2 add 9 is 11. -2, that's -8. -8 add 6 is -2. Add 9, 7. Oh. So rise over run guy is 1. So there's at least one place on this cubic in the region -2 to 2 that has a derivative of 1. So let's find the derivative. Power rule, 3x squared, take away 3 equals 1. Okay, I want to solve this quadratic equation. When is this equal to 1? As long as you do it to both sides, it's okay rule. Tell me what to do to both sides then to get closer to the answer.
Add 3.
So I would do. What would I do to both sides to get x squared on its own?
Divide by 3.
And what should I do now to get the x?
Square root both of them.
And when you do square roots, remember the plus or minus one, right? And it might be that one of these gets kicked out because it's not an interval. Might be both are okay. So the two choices that we have are a negative square root of 4/3, and the other one is a positive square root of 4/3. I'm going to try and make that a little bit prettier. You may want to put them into calculators, but can you trust me, both of those work, right? Both of these are inside that interval. So there's two guys. So in C, you would write down that guy, comma, that guy. And that's exactly what they're wrote for.
Do we not have to rationalize the denominator?
I would, but Weber saying didn't. I would just do it as just normal. So it's I would be really happy with that. But Weber sign would take that. Sometimes even I don't always rationalize the denominator because I forget it. Right? But I'm old and I forget lots of things. Can you hear a squeaking sound at the background? Do you know what the squeaking sound is? Come here. It's this little girl here who found her squeaky pig again. And I keep hiding it, and she keeps finding it. Right. What? Okay, there you go. And to show you what my wife does to our poor animals, this thing is where the squeak's coming from. As far as I can tell, it's a unicorn. But it's kind of missing bits of its body because this little vicious little character eats it. Go on, go get it. Right. God, I'm so easily distracted. Are we cool with this question? Right, mean value theorem. I like questions that have a flow to them. Would you agree these questions kind of do the same thing? You just change the equation a little bit. You know she's doing that to annoy me now. She's brought it back. No, we've done that one. Okay, let's do a question that doesn't involve polynomials. So this one is question 12. Oh, perfect timing. This is our last question. So we finish this one. We're kind of done with that section. So, well, almost. There's a couple of things. Hey, I'm working here, you guys. Yeah, go on. Come on, move. Let's go. Up, up, up. Yeah, come on. There you go. Yeah, yeah. Come on. Hey. Come on. Oh, come on. Come. I'll forget it. It's like herding snakes. You push one out the door and the other one comes in. So let's just keep going. I'll survive. We are going to do the mean value theorem on this function. Now, if you sketch the log function in Desmos, it looks like that. But as long as you stick from 1 to 9, would you agree the log function is a pretty boring curve? So it is differentiable and it is continuous, right? At least from x is 1 to 9. So I can use the mean value theorem. I'm going to calculate this guy. So it's going to be f of 9 take away f of 1 over 9 take away 1, because that's a and that's b. And f of 9 is the log of 9 take away the log of 1 all over 8. Now I can make that a little bit prettier. Does anybody know what nice number the natural log of 1 is equal to? The natural log of 1 is a really nice number. What is it equal to?
This has to do with E, doesn't it?
Yeah,
Just 0, right?
it is 0. What power of E gets you 1? The answer is 0. So if you're thinking what a log is, you're actually finding what power of E gets you that number. And so it's 0. So the bottom line is that this fella is equal to that. And so we now need to find the derivative. And for a natural log function, the derivative is just 1 over x. And so we are trying to find out when is 1 over x, the derivative, equal to the natural log of 9 over 8. Okay. Anybody want to tell me what would be a good algebraic thing to do next?
Cross multiply.
I would. So x times the natural log of 9 is 1 times 8. What would you do next? Don't worry about log of 9. Think of it as 4. What would you do if it was 4x equals 8?
Divide by 4.
Okay, so in here, this case, you divide by log 9. That's all. And that guy is your C. I guess I should check, but can you trust me that that guy is a number somewhere between 1 and 9? And I know it is. You're done?